Dear students, in last class we discussed statically induced EMF and dynamically induced EMF. In today's class, we shall discuss series magnetic circuits. To understand series magnetic circuit, let us see how an iron ring is made from a iron rod. We can have iron rod having a cylindrical shape or a shape of cuboid. In cylindrical iron rod, let us say the length of the rod is L meters and the diameter of the rod is D meters. In case of cuboidal iron rod, say the length of iron rod is L meters and the cross section is square having the side length B, or the thickness of the rod here is B. In case of cylindrical rod, area of cross section is calculated as pi into d by 2 whole square or pi d square by 4. And if radius is given, then area of the cross section of rod will be equal to pi r square. Radius of cross section r is equal to d by 2. Therefore, we can write area of cross section as pi r square also. In case of cuboidal rod, area of cross section is square of the thickness of bar, that is area is equal to b square. Unit of area is meter square, so you show here meter square and meter square. Here also you show meter square. Now if we bend these bars and make a ring out of it, that ring would appear like the one shown here, and this ring is called as iron ring now, because we have made use of iron material in making the rods here. If I cut this ring, then I get cross-sectional area. If cylindrical rod is used in making iron ring, then area of cross-section will be circular. And if cuboidal bar is made use in making the iron ring, then the cross-sectional area would be area of the cross section of the rod, that is b square. In making iron rod, instead of using a square cross sectional rod, we can also use rectangle shaped cross sectional rod. In that case, the calculation of area of cross section formula will change. You all know that area of rectangle is B into L. We all know that iron is magnetic material, that is, it can be magnetized by setting up flux in it. Then how do we set up the flux? For that we need magnetomotive force. Now you look at the iron ring here. On this iron ring, a winding is made and number of turns in the winding are equal to N, and current of 5 ampere is allowed to flow through the winding. We know that by applying thumb rule we can find the direction of magnetic flux produced by a coil. That is, if we hold a coil carrying current in our right hand in such a way that the direction of the current through the coil is indicated by all the fingers of right hand except the thumb, then the thumb will be indicating the direction of magnetic flux. If I hold this iron ring in my right hand in such a way that all my fingers give the direction of current flowing through this winding, then the thumb will give the direction of magnetic flux. Therefore, we get the direction of magnetic flux clockwise in this iron ring. Since magnetic flux is set up here, this iron ring with a coil wound on it and current flowing through that coil is called as a magnetic circuit. So this is what now? This is magnetic circuit. We can increase the flux setup in this magnetic circuit either by increasing number of turns for the same amount of current flowing through the coil, or by increasing the current flowing through the coil for same number of turns, or by increasing both, because we know that flux phi is directly proportional to the magnetomotive force, that is N into I, or phi is equal to N into I by S, where S is reluctance. The unit here is Weber. This is called a series magnetic circuit because it has got only one flux path. Like in case of electrical circuits, we can have parallel magnetic circuit also. We will call this as series magnetic circuit. Now I will show you parallel magnetic circuit. The figure here shows a parallel magnetic circuit. You can observe here that the winding is placed on the central leg of the magnetic circuit. The flux set up here by the winding in the central leg will divide into two paths. which means that there are two paths for the flux setup. Hence it is a parallel magnetic circuit. If about the axis of this central leg, there exists symmetry in the magnetic circuit, material wise and dimension wise. In that case, the flux will divide equally into the two paths. That is, if the total flux setup is phi, total flux setup in the central leg is equal to phi, for symmetrical magnetic circuit, about the axis of central leg, flux divides equally in two paths. That is, flux setup in right leg equal to flux setup in left leg equal to total flux phi by 2 Webers. Here in series or parallel magnetic circuit, to calculate flux, we have to calculate reluctance, and that reluctance S is nothing but L upon mu into A. Here L is average length of the magnetic circuit. L is average length of magnetic circuit. I have explained how to calculate area A already. Then what is average length of magnetic circuit? Average length of magnetic circuit is nothing but the length of axis of the iron rod that is being used in making the iron ring. And about this L already we have discussed. For your understanding, I will show here the axis of the two rods that we considered in the beginning. And in this ring, we can show that average length L as another dotted circle exactly in between the two solid line circles. So this length gives us average length of the magnetic circuit. Similarly, in parallel magnetic circuits, to know the average length, we have to add the length of axis of each limb. Now, we will solve one problem on a series magnetic circuit. Problem reads like this. A magnetic circuit having a circular ring shape is made from an iron rod. The cross section of iron rod is 20 centimeter. On the iron ring so formed, 500 turns of copper conductor are wound, and through these turns 2 ampere of current is allowed to flow. If relative permeability of iron used is 800, calculate the flux setup, flux density and magnetic field strength. Solution. Given diameter of cross section, small d equal to 5 millimeter. This will convert into meter. 5 into 10 raised to minus 3 meter, because we need all lengths in meters. Average length of magnetic circuit, L is equal to 20 centimeter. This also we will convert into meter, and it will be now equal to 0.2 meter. Number of turns in the coil, N is equal to 500. Current flowing through the coil or winding I is equal to 2 ampere. Relative permeability of iron mu r is given as 800. We have to calculate flux density and magnetic field strength. Calculation of area of cross section. We are given with a cylindrical iron rod having diameter of small d. Using this d, we can calculate radius of iron ring, which is equal to radius of iron rod. That is equal to half of d and is equal to 5 into 10 to the power minus 3 by 2 meters. That is 2.5 into 10 to the power minus 3 meters. Therefore, area of cross section of iron ring A is equal to pi into r square. That is equal to pi into 2.5 into 10 raised to minus 3 whole square. Unit is meter square. On simplification, we get, making use of calculator, pi into bracket 2.5 into 10 raised to minus 3 bracket whole square. That is equal to 1.9634 into 10 to the power minus 5. Give the unit as meter square. Always try to keep the exponent part of your answer as 10 raised to minus 3, 10 raised to minus 6, 10 raised to minus 9, 10 raised to minus 12, or 10 to the power 3, 10 to the power 6, and so on. For that purpose, you are having ENG button in your calculator. If you now press this button once, your answer will be now having exponent part as 10 to the power minus 6. That is, your answer becomes 19.634 into 10 to the power minus 6 meter square. Now we'll calculate the magnetic field strength. So right here, calculation of magnetic field strength. H equal to N into I by L by definition. That is equal to 500 into 2 divided by 0.2. On simplification we get H equal to 5000 ampere turn per meter. Next we will calculate the flux density. So right here, calculation of flux density. B equal to mu H. Mu is calculated as mu naught into mu r, and H value we know, we have to substitute that. Mu naught is constant, that is permeability of free space, which is given as 4 pi into 10 to the power minus 7. Mu r is given as 800, and we have calculated the magnetic field strength H as 5000. So on simplification we get 5.026. Unit is Weber per meter square or Tesla. Next we will calculate flux setup in the magnetic circuit. Calculation of flux phi. We know the relation between flux and flux density, that is flux is equal to flux density into area of cross section, that is 5.026 into 19.634 into 10 to the power minus 6. On simplification we get 98.691 microweber. Now we will take second question. This second question is modification of the first question. Keeping all the data fixed, now we have to insert one small air gap in this iron ring and then calculate flux setup in that air gap. So right here, in the above problem, insert an air gap of 0.1 millimeter in the iron ring and calculate the flux setup in the air gap. Solution. First we'll write given data. Length of iron ring Li is equal to 20 centimeter minus length of air gap, say Lg, because when I cut one air gap in the iron ring, the length of the iron ring will reduce by the length of air gap. So 20 centimeter means 20 into 10 raised to minus 2 meter minus 0.1 into 10 raised to minus 3 meter. Because it is in mm, we have to convert the lengths into meters. On simplification we get 0.1999 meter. Length of air gap Lg is equal to 0.1 into 10 raised to minus 3 meter. Number of turns N is 500. Current through the coil I is equal to 2 ampere. Area of cross section, I will not repeat the calculation here. I will write it from previous calculation. That is equal to 19.634 into 10 to the power minus 6 meter square. Relative permeability of iron is given mu r, but here I will call it as mu ri. What it is? Relative permeability of iron. How much is its value? It is 800. Relative permeability of air, I will call it as mu Ra, and that is equal to 1. Now we will calculate the magnetomotive force. Calculation of MMF, that is N into I equal to 500 into 2, that is equal to 1000 ampere turns. Now it is a series magnetic circuit having two materials in it. One is iron and another one is air. Let us show that circuit here now before we proceed further. So here now you can see iron ring with small air gap. This is nothing but air gap here, Lg, and its length is 0.1 into 10 to the power minus 3 meter. Length of iron part is equal to 0.1999 meter. Now on this iron ring we are having a coil with 500 turns through which a current of 2 ampere is flowing. Right? Now we have to calculate here how much flux is set up in the air gap. The flux set up in the air gap and the flux set up in the iron part will be same because it is a series magnetic circuit. Calculation of flux in the air gap. We know that in series circuit flux is constant in all the parts. Since in the given circuit area of cross section is uniform, flux density is also constant in all the parts. that is flux density in iron is equal to flux density in air gap is equal to B. Say. All right, knowing magnetic field strength H is equal to magnetomotive force per unit length, we can write N into I equal to H into L. Since there are two parts in series magnetic circuit given to us, that is iron and air gap, we will write magnetic field strength H into L as HI into Li plus Hg into Lg, that is equal to N into I. Hi is magnetic field strength of iron part, Hg is magnetic field strength of air gap, Li is length of iron part, Lg is length of air gap. But we know the relation between H and B. What is that? B equal to mu H. Therefore, we can write H equal to B by mu. The permeability of different parts in the series circuit will be different if materials are different. Therefore, we can write now here B upon mu I into Li plus B by mu G into Lg, where mu I and mu G are permeability of iron part and air gap respectively. Taking B common outside, we can write inside the bracket Li upon relative permeability of iron into permeability of free space plus Lg upon mu Rg into mu naught. In denominator, mu naught is common, so we will take mu naught outside and write B by mu naught into the bracket Li by mu Ri plus Lg by mu Rg. Now we will substitute all the known values. N into I is 1000, we have calculated. B we don't know, keep it as it is. Mu naught is 4 pi into 10 to the power minus 7. Li is 0.1999 meter. Mu Ri is 800 plus Lg is 0.1 into 10 to the power minus 3 meter by 1, because relative permeability of air is 1. Simplifying for B, we get 3.592 Weber per meter square or Tesla. Therefore, flux in air gap phi z equal to flux density in air gap B into area of gap. In the given problem, iron part cross sectional area is equal to air gap cross sectional area. Because air gap is cut in the iron part. Substituting and simplifying, we get .534 microweber. You can see here the flux value is lesser comparing to the flux value in the first problem. It is so because when air gap is introduced, the reluctance of the circuit increases and hence the flux value comes down. Dear students, I will stop the class here and continue in next class. Thank you.